So here we have an example of a fifth order or quintic polynomial, and we want to find all the roots. Now if you have a look at it, we can't really use factoring or grouping or any of those methods, so we need to have a look at the rational root theorem. Now what that entails is finding the factors of the leading coefficient and the factors of the constant. So I'm just going to do two columns P and Q. So P are all the factors of my constant, and they are -5 and 1 and 5 and -1. The factors of my leading coefficient 1 is 1, and -1 is also a factor because -1 times -1 is 1. However, because we already have the exact terms in a negative and positive as P, we don't need to consider it. Then I'm going to work out P over Q 1 by 1. So -5 divided by 1 is -5, 1 divided by 1 is 1, 5 divided by 1 is 5, and -1 divided by 1 is -1. Then what we need to do is find out which of these, when substituted into this function, equals 0. Because if it equals 0, it is a root of the function. Now I always like to start with my lower numbers first, just because I find them easier, but it really makes no difference. Now if I have a look, if I want to apply Descartes' rule of signs, and I run from the left to the right, I do have a change from positive to negative, therefore I have a positive root, and if I make all my x's the function of -x instead, I also have a change, so I also have a negative root. So that doesn't really help me in this instant. I'm not going to be able to eliminate any of these possibilities here on the left. So let's try 1. So 1 to the power of 5 minus 3 times 1 to the power of 4 minus 8 times 1 cubed minus 8 times 1 squared minus 9 minus 5 is not equal to 0. Therefore, this is not a root of the function. Let's now try -1. So that's -1 to the power of 5 minus 3 times -1 to the power of 4 minus 8 times -1 to the power of 3 minus 8 times -1 squared minus 9 times -1 minus 5. So we're going to get -1 minus 3 plus 8 minus 8 plus 9 minus 5. And if we put all of that into the calculator, we end up with 0. Therefore, -1 is a root of our function. Since -1 is a root, we can say x plus 1 is a factor. And I'm just going to leave that up there because I'm going to divide by -1 using synthetic division to find our next polynomial. So I put the -1 out the front, draw my division box, and then bring down all my coefficients. Now when doing this, remember to check that your exponents are decreasing by 1 only so that you know you don't need to put any zeros in the gaps. If they don't, for example, if this term wasn't here, you'd have to put a 0 for the coefficient of x cubed. Okay, so we just write all the coefficients. So 1, -3, -8, -8, -9, and -5. And the first one always drops, and then that's the one we start with. If you've never seen this before, it's a very repetitive process, and it's very straightforward. We just multiply these two terms. -1 times 1 is -1. Then we add each resulting column. -3 minus another 1 is -4, and repeat. -1 times -4 is 4, -8 plus 4 is -4. -1 times -4 is 4, -8 plus 4 is -4. And we keep going in this fashion until it is finished. Once you get a 0 here, this means there are no remainders, and we don't expect any remainders because we know that -1 is a root. So these coefficients here form the coefficients of our answer, and our answer is the same exponents as above reduced by 1. So this is going to be 1x to the power of 4 minus 4x cubed minus 4x squared minus 4x minus 5. Now looking at that polynomial, again, it's not an easy one to find the roots of, so we're going to have to use the rational root theorem again. So for this new polynomial, we again need to find the values of p and q. So we look at the leading coefficient and the constant. The factors of -5 are again -5 and 1, and 5 and -1. And over here we have 1 and -1, but we don't need to worry about -1 because we have negative and positive of every term in p. Then we need to do p divided by q, and we end up with exactly the same as we had before. I'm going to try the smaller numbers again first for ease. So if I do 1, I get 1 minus 4 minus 4 minus 4 minus 5, and that does not equal 0. Therefore, 1 is not a root of this new function. So let us try -1. We get 1 minus 4 minus 4 plus 4 minus 5, which does equal 0. Therefore, -1 is a root of the new polynomial. Since -1 is a root, it stands that x plus 1 is a factor. So we now have two x plus 1 factors. And again, we need to perform a division. I'm going to do synthetic again, so -1 out the front, do my division box, and then bring down all my. So put the coefficients in. We've got 1, -4, -4, -4, and -5. As you know, we always drop this one, and then we start multiplying. -1 times 1 is -1. Add this column, and we get -5. -1 times -5, obviously that's going to be +5. -4 plus 5 is 1. -1 times 1 is -1. -4 minus 1 is -5. As you can see, it's very, very repetitive, and again we end up with 0 as expected because we already knew it was a root. So these numbers down here form the coefficients of our answer, which is 1x cubed minus 5x squared plus x minus 5. This cubic polynomial can easily be factored by grouping. I'm going to group the x cubed and the x together, and the -5x squared minus 5 together. So for these two terms here, I'm going to take x out the front, and I end up with x squared plus 1. And for these two terms, I'm going to take -5 out the front, and again I get x squared plus 1. And that's how you know that grouping has worked, because you end up with the same bracket. So the overall factors are x minus 5 and x squared plus 1. So if we put all our factors together that we have x plus 1, x plus 1, x minus 5, and x squared plus 1, which isn't linear, but we can make this a difference of two squares by making it x squared minus -1, which makes it become linear as x minus I and x plus I, because the square root of x squared is x, and the square root of -1 is I. So our answer finally to this problem, what the roots are of the function, is going to be -1 with a multiplicity of 2 because it occurs twice, 5, I, and -I. And we should end up with 5 complex roots, and indeed we do, because we always count the multiplicity, and we have -1 of a multiplicity of 2, so we can be confident that we are correct. If you wanted to double check that you were correct, you could always expand all of these brackets, and you'll end up with the original polynomial you started with.